Some 4 years ago, when Anne-Marie Madigan first encountered the idea that there might be an undetected massive planet lurking beyond Pluto's orbit, she felt excited but skeptical. The evidence for such a world was then, and now remains, circumstantial. Strange patterns in the orbits of small objects at the outskirts of the known solar system. Proponents of Planet 9. Pluto no longer counts in the solar system's planetary tally, say such patterns could be produced by that world's hefty gravitational influence. But Madigan, an astrophysicist now at the University of Colorado Boulder, wondered whether some other, more prosaic explanation could suffice. At the time, she was studying how stars can jostle one another into different orbits as they whirl around supermassive black holes. And she saw no reason why her work could not also apply to near things orbiting our Sun. Today, from those modest beginnings, Madigan and a few of her collaborators have developed a totally different theory to explain the strangeness in the outer solar system. The collective gravity of a diffuse, sprawling, and so far largely hypothetical disk of icy debris far beyond Pluto could alter the orbits of the far distant objects we readily see in a way that resembles the effect of a large planet. Such a disk would be composed of millions of small bodies, most of them left over from the solar system's formation long ago. What we're doing is taking the gravitational forces between all these small bodies into account, Madigan says. Including those gravitational forces turns out to be really important, provided the putative disk possessed sufficient mass, several times that of Earth. Over 1 billion years or so, the tiny gravitational interactions between and from its constituent members could sculpt the trans-Plutonian outer solar system in ways otherwise explained by Planet 9, she maintains. The effect would be a bit like the proverbial butterfly flapping its wings to eventually set a distant storm in motion. Madigan and her graduate student Alexander Zadarik have now advanced their theory in 2 new studies posted on the preprint server archive.org. In one, submitted to the Astronomical Journal, they show how collective gravity can produce the same kinds of tilted and clumped orbits seen in about a dozen objects at a distance 250 times that between Earth and the Sun, an observation others had attributed to a possible Planet 9. In the other paper, under review at Astrophysical Journal Letters, they argue that given enough time, collective gravity can also explain how certain objects in far-out orbits can shift as they twirl around the Sun, which had been taken to be evidence for an unseen planet as well. From this work by Madigan and her team, an alternate picture of the solar system's plausible history is beginning to emerge. In the early days, Jupiter, Saturn, Uranus and Neptune coalesced in compact, orderly orbits, somewhat closer to our star, which only migrated outward later because of gravitational interactions. Back then those worlds were surrounded by a swarm of leftover chunks of debris that never found their way to planethood, icy bodies that the giant planets eventually kicked outward. Most were left ostracized in what Madigan calls a primordial scattered disk, beyond the territory of present-day Pluto. And she suggests that there may be much more mass in the disk than other researchers have usually considered. The icy bodies were propelled into that ring with far from circular orbits, making up an unstable system, much like a wobbly, precariously spinning top. This system exerted gravitational effects while it gradually settled down into a more stable configuration, with some orbits sharing similar planes and orientations. That configuration would, of course, essentially mirror what one would expect from the hidden gravitational hand of an undiscovered large outer planet. The fact that collective gravity can give you all the key observational features means that you don't need anything new. I think Occam's razor would lead you to believe that it's the simpler solution than Planet 9, Madigan says. California Institute of Technology astrophysicists Mike Brown and Konstantin Batygin have been two of the foremost proponents of the Planet 9 hypothesis since they released a sensational study on the subject in early 2016, and they have also been honing their arguments for the world's existence. To match the latest observations, the researchers argue that Planet 9's mass must be between 5 and 10 times that of Earth, and its location must be between 400 and 800 times our planet's distance from the Sun, slightly smaller and closer than what they first proposed. Batygin says he is intrigued by Madigan's idea of a remote ring of debris. But he thinks that is not what the solar system looks like. If there were such a ring parked far away from our Sun, you run into the problem of its stability in the early solar system, since the solar system formed in a cluster of stars, he says. Perturbations from passing stars will mess up this ring. They're going to destroy its coherence and disperse it. Madigan resolves this problem in her new simulations with careful tweaks to timing. If the scattered disk assembled after the young solar system left its stellar nursery and the giant planets formed, it could endure for eons. Such tweaks are not trivial. Accurately modeling the collective gravity of a debris disk requires tracking the motions and interactions of thousands of particles or more floating and whipping around in computer models for the equivalent of hundreds of millions of years. That task is far more arduous than modeling the effects of a single planet, Madigan says, which is, in part, why she and her team so often seem to be one step behind the pro-Planet 9 contingent. To date, Madigan's idea has not gotten much attention in the scientific community, compared with Planet 9. But as telescopic searches for the planet continue to come up empty, that situation may be about to change. We're in a minority, but we're growing, she says. In the solar system, collective gravity just hasn't really been studied. The field is just starting to take off. At least two other research groups have also begun investigating various gravitational effects and dynamics as an alternative to Planet 9. They similarly involve either a disk of rocky bodies or a smaller number of larger ones whose gravitational influences, billions of years ago, could have also shaken up the early solar system to create the peculiar orbits of post-Plutonian debris. The attraction of what Madigan is doing is that it's a radically different way of trying to explain what's going on with these distant orbits, says Scott Tremaine, an astrophysicist at the Institute for Advanced Study in Princeton, NJ. He points out a challenge for Madigan's proposal, however. Her collective gravity hypothesis requires the scattered disk to have so many icy bodies that they add up to a rather large mass. Unless, at some point, the disk had a combined mass that was about 20 times Earth's and a location that ranged around a few hundred times our planet's distance from the Sun, it would lack the heft to sufficiently reconfigure the outer solar system to reflect what astronomers currently see. By following the orbits of comets, astronomers have already gained a fuzzy idea of how much mass must be out there. And a disk big enough to make Madigan's idea work lies at the upper end of what appears possible. In the contest to explain astronomers' observations of the anomalous clustering in the outer solar system, there is another, dark horse candidate in addition to collective gravity and Planet 9. Perhaps both hypotheses are wrong. Perhaps, in fact, there is no clustering at all. Biases in astronomers' methods of searching for small bodies and in the statistics used to study them en masse can lead to markedly different conclusions, some of which dismiss the observed clustering as illusory. With the Outer Solar System Origins Survey, we don't have strong evidence for clustering, says Michelle Bannister, an astronomer at the University of Canterbury in New Zealand and a member of that collaboration. The survey's design made it possible for her and her colleagues to spot extremely faint bodies that were not seen before and to more systematically assess whether they are clustered in an unlikely configuration. The distant objects they found could simply be part of a larger population that is evenly spread out. New findings by members of the Dark Energy Survey come to a similar conclusion, but they, too, have only discovered a handful of objects. The reality of small number statistics, of only seeing a few glimmers of patterns in structures in the vast darkness, is what makes it extremely difficult to test ideas about the outer solar system, including searches for a concealed planet or a disk of scattered bodies. Everything spotted there so far is faint, dark and small. Many are so remote, they take millennia to complete a single revolution around the Sun, making it far harder for astronomers to efficiently determine the properties of their orbits. In addition to explaining observations that have already been made, Madigan and her colleagues have begun making predictions. If they are right, there should be a huge gap in the distant objects' orbits, a region almost entirely swept free of debris and approximately centered at 50 times Earth's distance from the Sun. If Planet 9 exists instead, there should not be such a wide gap. I'm delighted to see that as the depths of the solar system get mapped out, it's creating this kind of theoretical enthusiasm and innovation. Bannister says, referring to both collective gravity and Planet 9. While Madigan, Batygin and other astrophysicists marshal additional pieces of indirect evidence to make their case and look for new predictions to test, they are also waiting for observations from more sensitive upcoming telescopes in the hope of directly settling the debate. The Vera C. Rubin Observatory, being built atop a desert mountain in northern Chile, will map small objects in the outer solar system to much greater depth and precision than before. And the telescope will see first light as early as fall 2021. Something really odd is going on in the outer solar system, and there has to be more mass out there. If our hypothesized disk is not observed with the Rubin Observatory, it's not there, and then it's Planet 9, Madigan says. It has to be one or the other.